All right. Okay. So there are two addresses. One is LBA is just like the virtual address in the OS, and PBA is just like the physical address in the OS. But actually, these two addresses, there is no relation between like operating systems. I mean, those addresses are dedicated inside the SSD, so there is no relationship between the operating system and FTO design. Okay. So when we are going to update this LBF 500, actually what we are going to do is we'll find a new block in we'll find a new patch in other blocks. So like this, if there is a new patch in block 2, then we will read out the patch from block 1, and then we'll modify those bits that we are going to update to. So in this example, we'll update to the red bits here. And then we'll write into a new patch in block 2, for example. So at the same time, we will update the patch mapping relation. In this example, like we move the PBA from PBA 800 to PBA 1201. Then actually they are using the same LBA because the virtual address, I mean the logical block address doesn't change. The thing that changes is the physical block address. Okay, so we change the physical block address and left the LBA becomes the same. And in this scenario, actually, user applications or user programmers, they do not really know what happens inside the SSD because all these kind of remodified write, they are finished by the SSD controllers. So the CPU inside the SSD. So the next time, if a user is going to read out like LBA 500, then SSD controller will help to do the remapping and to find out actually LBA 500 is now remapped to the PBA 1201. Then the data stored on PBA 1201 can be read out. Okay, so this is how the remodified write be implemented inside the SSD. And this patch remapping or like address remapping is quite important because with using a patch address remapping, users do not really need to know what happens inside the SSD. Okay. So actually, we also point out there are some limited lifetime issues for SSD because each NAND flash cells there have their own lifetime, and the lifetime is because the capability for capturing the electron inside the floating gate, there is some limited there. For example, if one day like it is not possible to capture the electrons inside floating gate, then the NAND flash cells becomes worn out. So wheel leveling is also performed inside the SSD, but actually we do not really talk too much about this perspective because like I think this is a little bit advanced topic. So yeah, the thing you need to know is SSD will help to cells so to make all the NAND flash cells can endure very similar amount of the writes. Okay. So the second things that we need to talk a little bit more about is the how CPU access the peripherals. So we say there are two different ways for CPU to access the peripheral. First one is the port mapped I/O. So port mapped I/O CPU use a special instruction. In this example, we give the in and out instruction to access the I/O address. So for the memory address, usually, generally CPU use the low store instructions. So you can find like if we are going to use a port mapped I/O, we need another instruction set. Okay, so this will be another overhead there. And memory mapped I/O, I think you guys are more familiar with because memory mapped I/O is just to let I/O address to be mapped on the memory address space. So for the 32-bit systems, the memory address space, virtually there are kind of 32 bits, right? So we just reserve some of the bits on the 32 bits for the I/O address. So the good thing is actually CPU can use a low store instruction to access I/O address or memory address because they share the same address space. And the thing is, we don't really need another instruction set here. Okay, but But the things for the port mapping I/O is like this. If in like several decades ago, because we don't have that much of the address space. For example, in the 32-bit system, we can only address up to 4 gigabyte, right? 2 to the 32 is 4 gigabyte of the address space. So now if there's a lot of I/O device and they're going to share the 32-bit address space with the like memory device, in this case, we don't have that much of the space for using the memory mapping I/O. So several decades ago, people are using these port mapping I/O solutions to solve these issues. But now, I mean, now like in the recent like 10 to 20 years, actually we are moving from 32-bit system to 64-bit systems, and we have 64 bits of the address space for memory. So actually, we have a lot of luxury to use the for I/O address. Okay, I'll come back for DMA later because I have another new slides for the port mapping I/O and memory mapping I/O. So here are a little bit more details about how MMIO and PMIO for. So MMIO maps device register and buffers directly into the memory address space. So remember when we are talking about SSD, actually inside SSD there are also like DRAM buffer, those kind of things. And also for some device, there's register inside to control the device. So when the CPU is going to configure the device, CPU needs to access those register and buffer. And CPU can decide to use memory mapping I/O or port mapping I/O. Okay. So maybe you guys would be curious about why we need two different kind of I/O. I mean, actually, MMIO can do a really better job than port mapping I/O now, right? Because we have like 64 bits address space, so we don't really need port mapping I/O. But in terms of the compatibility, actually, early systems use PMIO for simplicity, and then we can save the like the memory address space here. But when we change to kind of powerful systems, if we don't want to kind of invent a new operating systems or like a new version of operating systems, then usually people or like usually the kernel developer will enable this capability. Compatibility. So actually, this is the reason why now there is still the support for port mapping I/O. But I mean, in most cases, current systems only use the memory mapping I/O. Okay. So here is also a table that I try to arrange about what's the difference between the port mapping I/O and memory mapping I/O. So I think there are some interesting thing I just marked it as a red. So in terms of the address space usage, as I mentioned, port mapping I/O, they have their own address space, not shared with the memory address space. So it can preserve a little bit of the memory space. I will just say a little bit because usually when we are using port mapping I/O, usually we only use like 16 bits or like 8 bits. So that this kind of consumption doesn't really matter a lot. But I mean, if you are using the 32-bit system, it really would be a case here. So for memory mapping I/O, just like I/O device and memory device, they share the same address space, so they do have some contentions with each other on the address space. And for the performance, usually, actually, when you are using port mapping I/O, there is some performance degrade here. The reason is you use two different kind of instruction set. So for CPU, then it needs to switch between these two instruction set. CPU cannot just use one like low stall to access memory and I/O. When CPU needs to switch between the instruction set, like when we're using the in-out instruction, then CPU needs to switch to in-out instruction. And when CPU is going to access the memory, CPU needs to switch back to a low stall. So CPU needs more time to decoding the instructions. Okay, so this is the reason why it takes a little bit more performance overhead for the port mapping I/O. And here's an example. I mean, for the same mouse and keyboard device, actually there are two different interfaces for mouse and keyboard, right? Currently, people are using USB-based mouse and keyboard. And for USB-based mouse and keyboard, they are all belonging to the memory mapping I/O category. But in ancient time, like there is PS2. So PS2-based mouse and keyboard, they're using a port mapped I/O. Okay, so they're the same device, but the different interface will make CPU needs to use different kind of protocol to support the I/O addressing. Okay, so there is about the port mapped I/O and like the memory mapped I/O stuff. And then let's move a little bit back to the DMA. So actually DMA is not really related to the using port mapped I/O or memory mapped I/O. Actually, DMA is another concept. So DMA, just like the figure shows here, DMA is we need another controller called DMA controller. And DMA controller can help to do the data transfer. So come to think about it, if there is no DMA controller, CPU needs to move the data by itself from the I/O device to the memory, right? So CPU will just store there or like synchronously wait here for the I/O completion. And it takes a lot of time because CPU cannot switch to other place. Okay, so DMA controller is here to solve this problem. So if we can have a controller, it doesn't really need to be so powerful in CPU. It can be a very like embedded, like low power, like CPU there, and it only the role of that DMA controller only for data moving. Okay, so CPU will offload the kind of data movement job to DMA controller by doing some configuration. What kind of configuration? CPU will let the DMA controller know which data address in the I/O device should be moved to the memory address. So for example, if we are going to move the 4 kilobyte data from I/O device to memory, then CPU will tell the DMA controller to say, hey, let's start to move the data from a certain I/O address. And then the size or the offset is how much, like 4 kilobyte. Then DMA controller, after getting these instructions, DMA controller will start to move the data like from I/O device to the memory. Okay, so after CPU like offloading this instruction to the DMA controller, CPU can do other things than just moving the data. CPU can do running other process like this. So DMA controller, you can think about it just like a delegations for CPU to move the data. And there is a question from you guys is about, then it sounds like DMA is a great solution for data moving, right? Because introduce this new hardware like controller, it can greatly alleviate the CPU overhead for data moving. It is true, but there are also some constraints for DMA. So actually DMA, because it is a very primitive or like it is a very like simple controller here. So usually DMA controller usually support to move the data in a continuous way. So there are several things that DMA controller will work not that efficient. For example, if we're going to move the small data, for example, if the data is like several bytes there, then because each time CPU needs to send the request to the DMA controller to move the data. So if CPU frequently send the request to the DMA controller, it takes time. So in that case, CPU can just move it by itself if the data is not that much. Okay. So there's another scenario is about the non-continuous data. So for each time, DMA controller can only move the continuous data. Because as I mentioned, CPU will only send the DMA controller the starting address and how much we are going to move. So if the moving is not continuous, then CPU needs to send a lot of DMA requests to the DMA controller. So it will take a little bit overhead here. But actually, in most systems now, we use the DMA for most of the cases, okay? Because like CPU's resource is quite important for the process and for most of the cases. So using more DMA controller is also a good trade-off here. Okay. So actually last time we didn't really give you some example about the device driver. So last time I just mentioned about actually in Linux kernel, there are 70% of the Linux kernels, they're all device drivers. So I just bring out the Linux kernel 2.6, and then there is someone do some arrangement about, hey, actually for there are some for character device, block device, and network device drivers, and all these they are belonging to the device driver. So like 70% of the kernel code, they are all from device driver. Just some one things to let you guys know. So okay, here is the things I'm going to add a little bit more for the device driver part. So come to think about if now we have a device, it is about the USB to Ethernet conversion device. I think this is you usually use this kind of device if you don't have enough like Ethernet socket, right? You will insert the USB to Ethernet conversion, this kind of device into your notebook, for example, and then your notebook can support the Ethernet. Okay, but how does this device work? So usually, like Linux or not Linux, like most of the networking, they follow the TCP/IP stack if you are going to send a TCP/IP request, right? So Linux also support this kind of TCP/IP protocol layer. So the thing is, when we are going to send this packet to the USB to Ethernet controller device, and there are usually two. I mean, there will be more, but I just make it simple. There are two here. One is USB to Ethernet driver, and the other is USB bus driver. Okay, so USB to Ethernet driver, there's some protocol that we need to follow for Ethernet family protocol, right? So if we are using TCP/IP, then there is some TCP/IP protocol. So the kernel code will encapsulate this kind of protocol inside the request, and then send into the USB to Ethernet driver. And then we have another encapsulate is because this device is connected with the PC or like with the notebook with the USB interface. So we need to encapsulate another layer is the USB driver layer. Otherwise, the packet cannot be sent into this through this kind of device. So we have USB driver to support these kind of things. Okay, so if you still remember, we mentioned about like actually device driver is going to communicate with the controller on the device, and then usually like we say there's a PCIe controller, there's a USB controller. Usually they are on the motherboard. Okay, because the motherboard like is the place you plug in your device. Okay, on the motherboard, there are several sockets there. There are USB socket, there are PCI socket, those kind of socket, they are all on the motherboard. So those kind of controller, USB controller, PCI controller, they are also on the motherboard. So to drive this controller can communicate with those kind of device, we need some kind of software, and that kind of software is the device driver. So you can think about after kernel encapsulate those kind of drivers and then start to move, actually this kind of packet will be first sent to the like USB controller on the motherboard, and USB controller will decapsulate or like resolve this kind of package and then send the USB to Ethernet driver to this inside this device. So the device can read out the protocol, can follow the protocol, and then to resolve this USB to Ethernet drivers information there. Okay, so then we will finish one like transmission from the device driver to the device itself, and this is how it works. And so like I think there's also a question is about how PCIe driver works, how NVMe driver works, and usually they are very similar. PCI driver is going to configure the PCI controller. Okay, so they also use this kind of driver kind of idea to implement it. Okay, so that is for that. So last time we spent a little bit more time talking about the buffer and the buffer heads, and also the block I/O. So I will quickly go through this kind of idea, and then jump into the file system part. So there are several keywords here. First of all, is a sector. So sector is the smallest addressable unit for a storage device in the system perspective. So no matter which kind of device, from the perspective of the block layer, actually they're using this kind of sector. So there are 512 bytes here. So you're using hard disk drive or SSD, it doesn't really matter because this is about the point of view from the block layer. It is not the controller inside the device. Okay, so here is a sector, and then when we say block, it's about the smallest addressable unit of the file system. So the relationship between the sector, block, and patch will be look like this. Like patch is larger than, I would say like no smaller than a block, and a block will be no smaller than the sector. But they can be the same size. For example, the block and sector, usually they can be the same size. Okay, so the thing is about like when we use the file system to allocate this kind of block, it is about the data on the store device, right? Because file system is going to manage the data layout on the store device. But when we are going to read out the data from the device, it must be read into the memory before being accessed. So there is the concept called buffer. When we move this kind of data from store device to the memory device, it is called a buffer. Cool. Okay, and because this kind of buffer in the memory, we need some ways to manage it. So for each buffer. Okay, so for the buffer head, there are several kind of information in here to describe the data. So here are about like what's the status of the data in the store device, and then where is the location of the data in the store device, all this kind of stuff. Okay, but we say like actually buffer heads, there are several issues here. So the first one is about it is large and bulky data structure because each buffer head contains all this kind of information and even more. Actually, I only drop part of it. Okay. Okay. But a block is smaller than a patch, right? Because we see a block is only 512 bytes, but a patch is 4 kilobytes. So it means like if we are going to maintain the size with the same size of the patch, for example, we need like 4 kilobytes for the patch, then we need 8 blocks to put in one patch, right? Because 512 byte times add is 4 kilobytes. So in this case, we need 8 times more this kind of buffer head to describe only one patch. Okay, so it spends a little bit more kind of space overhead to store this kind of buffer head data structures. So the first solution to solve challenge one is to directly work with the patch, not with the block for kernel. Okay. And the second one is about kernel should break up large block IO operation into multiple buffer head. And the reason is because we say each buffer head can only represent 512 bytes. Okay, so all these kind of challenges, they can be solved by the BIO structure. And BIO structure, it manages the block device not from the sector size. It is from the operations. What do I mean for operations? You can think about one structure BIO is one block request. So inside the request, there are several operations here. And what we define for operation is it should be aligned with the segment. So a segment means a chunk of the buffer that is continuous in memory. Okay, and it doesn't really need to be in what kind of size. I mean, it doesn't really need to be in 512 byte or like in what kind of size. So the reason is like this. For each BIO dash vector, you can think about for each I operations, we can control the data on the patch. Okay, so the segment, they can be larger than patch, or even it can be smaller than the patch size. Okay, so like this. The question will be like how to position or find the position of the segment. So for example, if the segment is in any place on this patch frame, so we need to record several things. The first one is which patch it is, and the second one is where is the offset, and the third one is what is the size of this segment. Okay, so for using these 3 parameters, we make the segment become so flexible. What do I mean? With these 3 parameters, the BIO structure can find out which patch frame store this segment. And then inside the patch frame, there are like 4 kilobyte, right? But maybe the segment size is smaller than 4 kilobyte, and it is not start from the very beginning. And if the segment starts from like this address, then we need an offset to position where is the starting point for the segment. So the offset is like this. Where is the starting point for the segment inside this patch frame? And the third one is how large it is. So we use this kind of length parameter to record about how large the segment is. Okay, so with these three parameters, we can easily identify each segment. Okay, so for the block IO request, it's submitted from the file system. For example, we will read out several kind of segments. Like we will read for the first segment for using this BIO dash vector, and then for the second BIO dash vector, maybe we are reading from another segment, or even we write to that segment. So we can combine several segment operations together with using only one BIO structure to describe it. Yeah, this is how like BIO structure differs from the buffer head. It is more flexible and it doesn't really need to consume that much of the address. Sorry, not that much of the storage capacity for memory, and also for using the BIO structures, it integrate with the patch structures. Okay, so this is about the BIO things. Last time we start at the BIO structure, so let's start from the following after the BIO structures. Actually, inside the Linux IO management, like in the block IO layer, there's a thing called request queue. So the request queue is going to store pending block IO requests. So you can think about it's about from the file systems, it submits a lot of BIO structures because there are several users there. So different users, maybe they submit one or two. So there will be a ton of block IO structures. So for the block IO structure, they will be stored in the request queue. Okay, so if we simply sending out requests to the block device in the order that the kernel issue them, then we don't really can enjoy the like locality on the data assets on the, for example, hard disk drive, because we say for hard disk drive, using the sequential access would be a lot of better than using the random access, right? Because hard disk drive, it uses the plate to rotate, and if we are accessing in the sequential order, then we can get a lot of performance benefit. But on the other hand, if we access the data randomly, then we cannot. So the thing is about, if we already know there are a lot of requests here, and each request there are several segments there. So is it possible to do some scheduling, just like how to minimize these six? Maybe we can merge and sort the pending requests in a queue, right? Because with this kind of request queue, I mean, there are several segments and maybe they are in the neighbor, then we can merge them together. But maybe they are from different block IO requests. So it is possible to merge different block IO requests and then to sort them to make it sequential. So hard disk drive can access those kind of, can finish all these kind of requests in a better format. So there's another idea called IO scheduler. It's going to solve this problem. I mean, it is possible to schedule this kind of block IO requests. And it decides the order of the request in the queue and at what time each request is dispatched to the block device. Okay, so there are several ways, just like it can coalescing two or more requests into one. And then we can sort the requests in a sector wise. I mean, the starting point of the sector, we can sort them. So after the sorting, we can minimize the disk seek and the rotation delay there. Okay. So this is about the overview about the IO scheduler, but I think we don't have time, so I didn't really put too much of the details about how to do the IO scheduler here. I mean, if you are interested in, we can have more kind of description for like the next like semester. We have another course talking about this kind of stuff. So okay, let's move on to lecture 5, file system and virtual file systems. So now we learn from the device, like we already learned about the hard disk drive and solid state drives, and also we learned about the device driver part and then the block IO layer part. So actually, until block IO layer, the design is still in the point of view of the how to make a good management for this storage device. So those are not designed for making user easy to access what kind of data. So file system, the goal for the file system is going to let the user can access the device or can access the data more intuitive. User doesn't really need to know what is block, what is sectors, and what is like storage device. Users only need to know file. And file is a virtual concept because before before file system in block IO layer and block device driver, we don't really name file there, right? There's no files in the block IO layers and block device driver. Okay, so from the disk perspective or the SSD perspective, there's no file concept here. Okay, so there are three main topics for a file system. The first one is file system itself. Just like there are different kind of file system, ext4, XFS, logback file system, those kind of stuff. And then there is patch cache. And then there are virtual file systems. So patch cache is more about if you are going to read out the data from a storage device. And maybe in the very recent times, you are going to reuse or like to access it again. Then we need a way to put those file data on the DRAM so we can reuse it. So this is the concept called patch cache. And then there's an idea called virtual file system. So virtual file system is more like actually in our system now, it can support using different kind of file system. For example, you can have your first disk using the ext4, the second disk using XFS, and the third disk maybe using like exFAT. So they are all using different file systems. Then in the programmer perspective, is it possible to access those different kind of file systems in only one like program, I would say like program paradigm. So it means like we only send the read request to each kind of file system, and each file system can work as it is. And this is how virtual file system works like. Just like all of the users, they only work with the virtual file system. And virtual file system will help to communicate with different file systems. So programmer doesn't really need to know, maybe I'm going to talk with the ext4, so I need to use ext4 instructions. And I'm going to talk with the exFAT, I'm going to use exFAT instructions. No, there's a little bit too complex. So this is about the virtual file system. But I think today we only talk about the file system part. So file system is a method and data structure that the operating system used to control how data is stored and retrieved. So without a file system, data will be one large body on storage media, and it is hard to separate and identify for the user because there are a lot of like segments, a lot of sectors there. So users doesn't really know maybe which sectors means what kind of data. Okay. And Linux supports many file systems here. So generally, there are two different perspectives for the file system. One is disk-based file system. So for disk-based, about to storing files on non-volatile block-oriented media. So there are ext family, XFS, exFAT, or even like Mac OS file system. They're all about the disk-based file system. Okay. And there is another very famous is called network file system. Okay. So network file system is the file might be on a different system carried out over network connections. So we need to know where is the file is. Okay. So maybe I think this is a little bit too abstract. So it is not really easy for you guys to understand. So I try to make one like example. Like if we analog the IO system to the library. So library users just like the applications. And if there are library users, they are requesting some books, for example, it means like application is going to get some files on our systems, right? So file system is just like the catalog systems. Catalog systems means like, for example, I'm going to find a book. So I know the title of the book. I know the authors of the book, and I know when the book is issued, for example. So those kind of information, they will be stored in these catalog systems. And then we can use this kind of information to find where the book is, right? We can use the author's name, we can use a title, we can use a date to do the filtering and then to get the books by using these catalog systems. Okay, so same as file systems. So we have a lot of files and they have different file names. And then they have their users only in these kind of files. So to get the file, to locate the file, we need this kind of file systems. But noting that actually the catalog system is just letting the library users or library staff know where the book is. We don't really get the book from the catalog system. It's just going to navigate the staff and users to know where the data is. So the library staff basically, oh, sorry, there's a typo here, retrieves the book from the correct shelf and slot, and they are analoging to the block layer and the device drivers. So the library staff just like a block layer, because library staff, after checking the catalog systems, it knows maybe it is on which shelves and which slots. So the library staff will go to get a book. And this is how block layer is. Block layer getting the information from the file system. As we mentioned, the file system will send a BIO structure to the block layer. So after getting the BIO, the block layer can locate about, okay, where is the data is, in which kind of disk, and the block layer will send to the device driver. So device driver here is just more like the way to get the data. Okay, and device is more like the correct shelf and slot. So device, you can just think about there's a lot of bookshelves. It is called device. Okay, so this is an analog between the IO systems and library. So once again, file system is just like the catalog systems. So it is, I would say, like it is a virtual layer between the users and the device. So device actually doesn't really know what is the file, and users, it only knows the file. Users don't know where is the data is, or like what is the location of the data, those kind of stuff. Okay, so this is for the file systems example. Okay, so let's talk about more kind of details about what is file system in the Linux perspective. So file is just like a linear array of bytes that can be read or written by the systems, because we are using the binary systems here. Okay, so actually each file inside in Linux system, it has a lower level name. It calls the inode number. So it uniquely identifies itself in the file systems. The reason is because for Linux system, it supports a lot of users to use the same systems at the same time, right? So different users, maybe they have the same file name file. But maybe, for example, they using the same file name, but the content is not the same. So we cannot directly use a file name as our identifier. For example, there are two users, and they just write, for example, txt for the file name. But for different users, txt, they may store different content. So if we directly use a file name as our identifier, then we cannot really uniquely identify the file content. So for Linux, actually, file name is not that important, because in the perspective of the Linux file systems, they only identify by the inode number. So each file has their unique inode number. Okay, but I mean, users doesn't really know what the inode number is. Okay, and I will show you how to do the conversion later. So in Linux, there's the second one. Special thing is about a directory is just a special type of file. So directory, when you are using like Windows and Mac, maybe it looks super different from the files, because the folder and file, there's two different concepts. But in Linux, actually, directory it is just a file. There's no difference between directory and file. Okay. So because each directory is just like a file, so each directory has an inode number as well. Okay. So you can think about a directory just like a directory file. Okay. So the third one is about Linux. Now they're using the directory tree to help to navigate where the data is. So the directory tree looks like this kind of stuff. So it always starts from the root. So the topmost node here, the backslash, means the root directory. And after the root directory, for each node here, we use a separator, and we use the backslash as a separator. Okay. So a file referred by the absolute path is from the root. So this is the definition for an absolute path. So like the path should always include the root directory. Okay. So in Linux, there's absolute path names, or like there is the referring path name there. Okay. So directories and files can have the same name. Just as I mentioned, actually, the name is not really important for the Linux. So directory are just like the files, and they can have the same name, but they will have different inode number. Okay. So when you are using Linux, you can have the like folder name and the files, they'll be the same. Okay. Okay, so you already know for Linux, there's no difference between files and directories. And also Linux doesn't care about the file extensions. So no matter you're using .pdf, .pptx, or like .txt, for Linux, it doesn't really care about what is the file extension it is. Okay. So let us dive a little bit more about the technical part. So when we the reason is about, like I said, no care is about the way to open the file is about there is a way, like there is application, there is a way to log about how to open this kind of file. For example, there is a link with the inode for that file. No, actually it's about like each file they have their own inode. And then for the inode structure, they will record about what kind of applications we can open this file. Okay. So actually the name is not really important. I mean, even you change the name, for example, in Linux, you change your name to from .pdf to like .pptx. But if you said about the default opening is using the PDF reader, you can still use the PDF reader to open it. So it is not about the link between the file name and how to open the application. Usually it is about, it depends, but I think it is about like link the inode and the how to open that applications. Yeah. So, okay. So let's integrate a little bit more about the process and the file. So there is a concept called file descriptor. So file descriptor is an integer to identify the open file in all file-related operations. And you can think about when you write a program and then you say you program you write a things called fread to open a file, and at the same time you will get a file number, a file descriptor there, and more like this kind of stuff, like this. So for different process, like if you are going to open a file, for example, this is the first file, and you will get one file descriptor called 1 or 3 or like 4. Okay, so usually the first few file descriptors, they are reserved for some important usage. For example, debugging usage, for example, the error handling, those kind of stuff, or like the read and the write, those kind of stuff. Okay, so but you can think about if you are going to open a file, then you will get like FD like 20 or like 19 or 18, this kind of stuff. Okay, and different process, they can have the same file descriptor because the concept for file descriptor, they're only inside the process. So different process, the file descriptors can be the same. Okay, so the file descriptor is assigned by the kernel when a file is open, and it's valid only within a process. Okay. So for the inode is another concept. Inode is about each file has just one inode, contains metadata such as access right, date, pointers to the file data. So inode actually it doesn't really only be a number. It is a data structure, and inside the data structure there's a field called inode number, and there's also more things than inode number there. There's access right, that pointers to the file data. Okay. So here's an example. If you have two processes and then you have the process open different amount of files there, and usually inside Linux there is a conversion table called open file table. So this open file table is going to link with the file descriptor with the inode number. Okay, so inode number, because like for a system, maybe you have a lot of disks. So different disks, you are going to store the data on it. Okay, so each data on a disk should has their own identifier, and this is called inode. So inode need another data structure to maintain it. Okay, but from the process perspective, for example, FD1, okay, maybe here, FD2 and FD2 in process A and process B, maybe they can point to the same inode. For example, this 73 here, they will be directly linked to the inode number 5139. So that means like process A and process B, even they're opening the data from different process, but they're opening the same file data here. Okay, so it is about like it makes the process has more flexible to identify each kind of file data. It's just like file descriptor you can think about just like a file name managed by the process. Okay, and how to link the file name to the file content itself is about there is an open file table and an inode table to help to link with the where the data really stored on the storage device. Okay, and inode table or inode structure means where is the location and what is the data stored on the storage device. Okay, so this is about some technical stuff for the file systems. Okay, so maybe we can take a 10 and come back later.